So what is the advantage of flowing more water during a flow test? While the procedures for running a fire hydrant flow test are fairly well laid out, we do have a step-by-step for us in NFPA 291 standard. There are plenty of points within the test that create error. Sources of error in a hydrant flow test include the gauge accuracy, our ability to read the gauge accurately, and gauge position and placement, among many other facets of the measurement process. One way we help combat these sources of error and give us more confidence in the results is to test with a flow rate that is beyond the flow demand of the system that we're working with. As a starting point, NFPA 291 recommends that we flow enough water to achieve a residual pressure that's a 25% drop from the static pressure, or flow the total demand deemed necessary for firefighting. As an example, let's look at a theoretical test with the same equipment but run at two different flow rates, one at about 400 GPM and one at about 1000 GPM. We'll go into the process of conducting a flow test and the step-by-steps in far more detail later. But as a quick recap, here's how we run a typical two hydrant flow test. We first have our test hydrant where we are monitoring the pressure at two different conditions. This is our static and residual hydrant because we are measuring our static pressure and residual pressure at this hydrant. For this module, we're going to refer to this hydrant as the test hydrant. We then have our flow hydrant, which we are using to flow water and see how the water supply reacts when there is a flowing condition. On this flow hydrant, we measure a pitot pressure so that we can estimate how much water we are actually flowing during our test. So our first step is that we open up and measure the static pressure from our test hydrant. Let's say in our test that the static pressure is 60 psi. We establish this pressure as the static pressure that's at a no flow condition. So let's chart this on our graph. Our second step is that we open up the flow hydrant until we have a somewhat consistent flow coming through this flow hydrant. In this first example, let's say we only open up the hydrant a little bit. At this flow hydrant, we measure the pitot pressure, which comes out to 6 psi, and simultaneously at this point in time, we take a pressure reading from our test hydrant. This pressure reading at the test hydrant is our residual pressure. In this example, our residual pressure is 57 psi. We then close out the test and slowly close the hydrants and clean up our mess. Hopefully we don't hurt any landscaping nearby. Again, we'll get into all of our tips and tricks and suggestions on flow tests in a whole lot more detail later. We can't just use this pitot pressure, however. We don't really care about the pitot pressure. What we're really interested in is the flow rate that we got during our test. So we have to convert the pitot pressure over to an estimated flow rate. We take the pitot pressure, combine it with a coefficient of discharge, and convert that pressure over to a flow rate that we had coming out of our hydrant. This is our residual flow rate. For this test, let's say we have a coefficient of discharge of 0.9 flowing 1 2.5 inch outlet with our 6 psi pitot pressure. That comes out to about 410 GPM. We'll cover this process and this calculation in a whole lot more detail later. Once we have our residual flow rate, which here is 410 GPM, and our residual pressure that was over from the test hydrant, which was 57 psi, we now have those 2 points that we can chart on our graph. Now, we use these 2 points to establish our hydraulic relationship in between them by drawing a straight line on a log graph. Now, let's say we were to run this same test. However, we're going to flow more water. We fully open the flow hydrant using 2 side outlets instead of just 1. We test our static pressure, which is still 60 psi, and we chart that on the graph. Then we open up our flow hydrant with 2 side outlets. Here we measure a pitot pressure of 9 psi with that hydrant that's now fully open. Our residual pressure with this much water flowing comes all the way down to 44 psi. Side note, NFPA 291 suggests that we drop 25% or more from that static pressure. This 44 psi residual pressure would have gotten us there. 25% of 60 psi means we needed to drop 15 psi. We did just a little bit more than that with this test by flowing the amount of water that we did. So converting the pitot pressure to flow with 2 outlets going, we have an estimated flow rate of about 1010 GPM. We take this flow rate with our residual pressure of 44 psi, and we now plot that on our graph. We can see here that the relationship is very similar. Well, it should be. It's the same water supply. So with a similar curve, a test at any point along the curve should show a similar relationship, although theory doesn't always perfectly align with the real world. Now let's see what introducing a little bit of error would have meant on these 2 tests. Just take, for example, the reading on a single gauge alone. If you've ever ran or witnessed a flow test, you know that analog gauges like to bounce around. It's not uncommon to have a needle that bounces maybe 2, 3, or 4 psi. Not only that, if you are using a 300-pound gauge and we're trying to distinguish between a 57 or 58 psi reading, well, that's extremely difficult to read. There's some error just in the bouncing of the needle itself. Now let's say that the gauge on the test hydrant is bouncing around and we mistakenly read 58 psi residual when we should have read 57 psi residual. This is just an example of what one slight measurement difference impacts our overall understanding of the water supply. Now, this is a 1 psi difference, or in this case, less than a 2% error in our reading. Let's draw this out on the graph and see what impact it has on our available water supply calculation. So here's our new curve with a slightly higher residual pressure. In between the static and residual readings, or in the range that we would consider to be an interpolation, this error is still very small. Let's say a system demand of 200 GPM, well, this error would only have made about a half psi or 1% difference in our calculations. However, while the error is small when we're interpolating, when we extrapolate points on the curve, our error becomes much larger. Let's say our system demand would be a dry, ordinary hazard group 1 system that's on a slope, and our system demand comes out to about 800 GPM. Well, now the error results in a difference of 3.4 psi, or nearly a 7% error. If we get into a dry and sloped OH2 system, or say we start to get into storage systems that have demands, say around 1100 GPM, well, now our error is over 6 psi off, and that's a 13% difference from the real water supply. Just a small difference in the reading here, because we're flowing so little during our test, is resulting in a very big error when we get higher and higher flow rates on the system demand. The more and more that we extrapolate beyond what our residual test point was, the more impactful any small deviation in our test becomes. If we were looking to calculate fire flow, our first reading at 57 psi residual would have us estimate the fire flow available to firefighters to be 1,670 GPM at 20 psi. Now with our slightly higher residual pressure at that 58 psi, we're now calculating a fire flow available to the fire department to be around 2,070 GPM at 20 psi. That's a 400 GPM difference, or that's a 24% error in the fire flow that we're calculating. The further from our data that we extrapolate, the more error we're going to get from even a slight deviation. Okay, Joe, but let's say we've got laser focused eyes, all of our test equipment is recently calibrated, our pitot gauge is perfectly centered in the middle of the flow, and we run a nearly flawless test. Well, what about that, Joe? Well, we still have uncertainty. A calibrated gauge can still be off by some allowable margin. Our measurements are really not perfect. They're still just a test with measurements that estimate a supply. The problem with flowing too little water is that any small deviation, whether it's our error or an error in the equipment or just the natural tolerances that go into a test, any small deviation or uncertainty is compounded when we later on extrapolate that data that's far beyond our measurement range. Now let's take that same small deviation and look at a second test where we are flowing, let's say about 1,000 GPM. So let's say we again slightly misread that bouncing needle and overestimate our residual pressure again by 1 psi. So in the test that has 1,010 GPM, we read a residual pressure of 45 psi instead of 44 psi. Let's plot and draw this new curve. Now this deviation has significantly less error than when we flowed less water. It's because our tested range is much wider. We are either extrapolating much closer to our tested range, or better yet, we're now interpolating. Again, interpolation means that we're taking a point between two known quantities. Extrapolation is when we're taking points that are beyond the range that we've tested. So let's say we've got that OH1 system demand of 800 GPM, which before, because of our mismeasurement, we had an impact of 3.4 psi or 7% error. But now, because we flowed more water, we're only off by 0.6 psi or just over a 1% error. That's far less error than when we flowed a small amount of water. That shows up in our fire flow calculation as well. Our fire flow estimates improve substantially. Our original curve, we would have estimated fire flow to be about 1,650 GPM. But now, even with a mismeasured residual pressure, our fire flow estimate becomes 1,710 GPM, or just being off by 3.6%. So because we flowed more water, our confidence in our results grows dramatically. Essentially, the real supply that we're going to be able to get out of those hydrants from the fire department is going to be much closer to our test results when we flow more water, when we work our way down that curve. Now, do we always need to run a hydrant flow test all the way down to 20 psi to figure out what the exact fire flow is? No, that's not usually necessary. It's also potentially harmful to the water supply, and in many cases, it's just not possible without a pump or multiple pumps pulling water out of the system. What NFPA 291 recommends is to flow enough water that our residual pressure is at least a 25% drop below the static pressure, or what the flow rate is for firefighting purposes. This gets our test results out far enough to give some confidence and overcome small deviations in the measured results. So, why is it advantageous to flow more water during a fire hydrant flow test? Flowing more water gives us greater confidence in the data and gives our results more tolerance from slight deviations or errors in the testing process.
This has been a preview of Meyer Fire University. Schedule a demo today at www.meyerfireuniversity.com.